SwayamPrabha. Digital India. Educated India.
Welcome viewers to the 8th lecture of the lecture series Metal Cutting and Machine Tools. So, in the previous lecture we have roughly had an idea how chips form and what are the ways in which we can estimate from looking at the chip how much is the deformation and what sort of other physical features are observable when we are looking at a chip like built-up edge formation, and what sort of analogies can be used in case of chips in order to find out where the deformation is taking place, and some calculations to find out how we can find out those angles related to geometric features related to the deformation. So, at the end of the now we are well poised at the end of the 7th lecture to look at the mechanics of the material cutting process. So, the 8th lecture, let us formally start. So, here first of all we see a chip coming out of the cutting zone in a particular direction, and you will notice that roughly I have indicated that the chip is coming out in the orthogonal direction. What is orthogonal direction? This one is the trace of the cutting plane seen from top, cutting plane or pi c. This one perpendicular to it and perpendicular to the reference plane must be orthogonal plane. So, I have drawn a figure in which I am claiming that the chip is coming down, coming out of the cutting zone by moving along the orthogonal plane. Now, you might place a question, what is the reason for which we make this assumption? Assumptions should be at least logical, that is okay. It is logical to make an assumption when we do not have the full picture. So, we now come across a term called orthogonal cutting. What is orthogonal cutting? Let us address it this way, that orthogonal cutting, in case of orthogonal cutting, the chips flow along the orthogonal plane. Now, is there any reason for which chips will not flow along the orthogonal plane? Yes, there are a number of reasons, and the major reason for which the chips might not flow along the orthogonal plane is that the inclination angle might not be 0. So, let us write it down. That is it. So, inclination angle means that if the cutting edge, as you can see here, there is the trace of the cutting edge as seen in the plan view. If the cutting edge is slightly upraised, inclined, so that its end point here towards this side is upraised with respect to the cutting point, or it is slightly down, in that case inclination angle is existing, and in such a case we will find that the chip will be deviating from the orthogonal plane, okay, moving slightly away. By how much? Maybe very close to lambda if we make some assumptions. Now, the second point is, are there other reasons for which the chip might be deviating from the orthogonal plane? And first of all, why are we so much hung up that orthogonal plane is something, orthogonal cutting is something special? Orthogonal cutting is a occurrence when the chips can when the forces can be considered to be contained in a two-dimensional plane, okay, and it is easy for us to visualize the situation and make force analysis, okay. So, let us come back here. So, we understand in orthogonal cutting, talking from mathematical terms, the forces will be contained in the orthogonal plane. What sort of forces are we talking about? The cutting forces. The cutting forces will be contained in the orthogonal plane. So, if the chip is flowing along the orthogonal plane, this is going to occur. So, now we ended up with the need for identifying situations where it may be otherwise. First situation was lambda is not equal to 0. In that case, the chips will deviate. What are the other effects? Other effect can be, for example, this particular auxiliary cutting edge which does part of the cutting, this sort of a material, it is removed by the cutting tool by the combined action of this cutting edge and that cutting edge. So, the auxiliary cutting edge also does some cutting, and if the chips emanating due to that cutting effect, they will have a chip velocity in this direction, while the component of velocity from the main cutting edge might be higher than that, but they will combinedly define a particular direction of resultant chip flow. Therefore, this is another possibility of deviation of the chip from the orthogonal plane. So, what we generally say is that the effect of auxiliary cutting should be negligible for orthogonal cutting to take place. Okay. Sometimes this is referred to as restricted cutting effect. Now, how can it be considered negligible? If phi 1 is equal to, is higher, just a moment. If phi 1 is higher than, oh my god, higher than 15 degrees, so that it is so much away from the actual profile that its cutting effect is much less. Okay. So, this way we define the conditions one by one. Lambda equal to 0, second, phi 1 is greater than 15 degrees, third, this angle, this plan approach angle should be between 0 and 90 degrees. (90° is greater than phi and greater than 0 degrees. Okay. And of course, there are other conditions like tool is sharp, there is no nose radius. If nose radius is present, it will make the cutting edge, have different orthogonal planes at different points, and they will contribute to the respective speed vectors from different portions, and there will be ultimately a resultant direction which might not match with this orthogonal plane. So, we are assuming that there is no nose radius and the tool is sharp, there is no edge rounding also. Once these these factors are accepted, we can assume that the chips flow in the orthogonal plane. Okay, let us have the next discussion. We sometimes refer to some cases as pure orthogonal cutting. What is pure orthogonal cutting? You know, if we completely remove the auxiliary cutting effect, I mean the cutting contribution of the auxiliary cutting edge, if it is completely removed from the picture, in that case, and also the other effects which are taking place, if they are completely removed, in that case we can have a situation in which purely orthogonal cutting is taking place with absolutely no interference from other factors. For example, if we now consider a pipe. So, this is a pipe which is shown in section. This is the material, this is hollow, it is rotating, and due to the rotation, this cutter, I mean due to the rotation, cutting is taking place, and this is the cutter. As the cutter is moving forwards this way, and say its cutting edge is so large that it totally encompasses the depth of cut. So, this material will be coming out straight, and there is no contribution of the auxiliary cutting edge. Hence, we say that effect of auxiliary cutting edge is completely absent here. So, pipe cutting, and also we will notice here phi is equal to 90. So, lambda is 0, phi is equal to 90, and there is no contribution from the auxiliary cutting edge. So, this sets the stage for the consideration of pure orthogonal cutting. There can be other situations also, one is as we have defined, second is this one. Our tool might also be poised to cut straight radially inside. We are cutting a sort of groove, say not just like this, this is the cutting edge, I mean tool, and this is the reduction in radius that we are cutting on a job, say this is the job, held on the chuck and rotating, and this is the way in which I am moving forward. So, if this is the feed direction, this is the cutting edge, and therefore, the chips are flowing 90 degrees to the cutting edge because lambda is also 0. So, radially reducing the diameter or longitudinally cutting a pipe, pure orthogonal cutting. So, next, when the chip is coming down the orthogonal plane, okay, and there is no angle on this side, which means, when there is no angle on this side, this is orthogonal rake angle. If this is 0, so that means sideways there is no tilt. In that case, the pull forces of this body coming down the inclined plane is only defined by the normal reaction and the frictional force, and therefore, it will be contained in this plane perpendicular to this particular plane. Okay. So, this is the cutting edge, this is our chip, this is the orthogonal plane, this one is the orthogonal plane, orthogonal rake is 0, sorry, I made a mistake. See, cutting edge is not supposed to have any inclination, so this is 0, and in that case this is orthogonal plane. The chip will be totally, forces on the chip will be totally confined to the orthogonal plane. Frictional force which the chip applies on the rake surface, and normal force which is existing as normal reaction between the chip and the rake surface. So, this is normal force, and they are totally on the orthogonal plane. So, having agreed about that, let us come to the different relationships which now exist for the resultant forces on the cutting tool. What do we mean by the resultant forces on the cutting tool? On the cutting tool, the forces which are being applied by the chip, they are normal force and frictional force. I mean, we can break them up into such components. There is a single resultant force. What we know about that force is that it is on the orthogonal plane. So, if this is, if this is pi O on the orthogonal plane, we are having the force, resultant force, that is the resultant of all interactions, resultant force if this is R, pointing upwards if we consider the force on the chip. The tool is applying this force on the chip. And what can it be, in what components can we resolve it? We can resolve it in components in the direction of the rake surface and perpendicular to it, in which case we will get frictional force, normal force representation. We can also resolve it in the standard, machine axis. Okay, this is the z axis and this is the force in the xy plane. Since it's the forces are restricted on the orthogonal plane, apart from the component in the z axis, the other axial components must be together in this plane. So, we are writing pxy. Pxy has to lie on the orthogonal plane in case of orthogonal cutting. In the same way, when we are talking about the shear plane, that means the plane in which the primary deformation is considered to be occurring, restricted in the form of shear. So, we can also consider a shear force to be occurring here, which is equal to, say, we are writing it as Ps and a force normal to it as Pn. If we have such a representation, all of them ultimately the resultant of F by N is resultant force, the resultant of Pz and Pxy will be equal to R, and the resultant of Ps and Pn will also be equal to R. We are simply resolving it in different mutually perpendicular directions and getting different interpretations about the phenomenon. So, let us have a quick look at the angular relationship. We have again considered gamma O to be positive, and this gamma O angle, it is equal to vertically opposite this angle. So, this is equal to gamma O. And what is this angle equal to? This angle is equal to gamma minus, sorry, eta minus gamma O. Eta is this angle. Okay. So, when we look at this one, what is this angle equal to? This is 90 degrees and this must be equal to 90 minus eta. So, let us write down 90 minus eta. Okay. So, let us have a quick check. Eta minus gamma O plus 90 minus eta, how much is that? Eta cancels, 90 minus gamma O. Yes, this is 90 minus gamma O. So, this matches with our calculations. So, this way we have the angular values of all these segmental angles, and therefore we can further establish another relationship between all these. Let's formally define them. Pz is called the main cutting force. Pxy is the cutting force in the I'll just rub it out. Thrust force. When you are doing longitudinal turning, in that case this force tries to push the job from away from the cutter. If phi is between 0 and 90 degrees, there is a push perpendicular to the axis of the workpiece. You might say, where is the workpiece? The workpiece is like this. Okay, this is the uncut chip. This whole work thing is the workpiece, which we have not drawn. This circle is not the workpiece, mind you. This is called merchant's circle, after the name of the scientist who established this relationship, merchant's circle diagram. So we come to the conclusion. So Pxy is called the thrust force. Next, so after that, Ps is the shear force along the shear plane, as we discussed. Pn is normal on the shear plane, and F is the frictional force on chip tool interface, and N is the normal force on the chip tool interface. This thing we have already defined. So let us move on to the relationships between these forces. First of all, we can establish a relationship between the resultant and some of these components in this manner. We can say the resultant force multiplied by cos eta minus gamma 0 is equal to Pz. Okay. So how do we establish that? Let's see. This is eta minus gamma O, and we are writing. Oh, I think we can do it in an easier manner than what is written. Okay. First of all, let us see what we have stated here. First of all, there should be another bracket here. Pz by sine. So we have used that particular formula, E by sine A is equal to B by sine B, that we can do. We could have also simply taken components. For example, if we write from here, R cos eta minus gamma O is equal to Pz, okay, which means Pz is equal to right. Which means R is equal to Pz by cos eta minus gamma O. And next, we could have also expressed the same relation between R equal to Ps shear divided by cos of beta plus eta minus gamma O. Why is this so? Because this is the angle, this whole angle is in between Ps and resultant. So R cos this angle is equal to Ps, which means if we combine these two, okay, if we combine these two, we get this relationship. Ps by cos beta plus eta minus gamma O is equal to Pz divided by cos beta, eta minus gamma O. From here we get an expression of Pz equal to Ps into cos eta minus gamma O divided by cos beta plus eta minus gamma O. So you might ask me that where has all this led us to? It has led us to an estimation of the main cutting force in terms of the shear forces occurring in the shear plane and some angles. Now, do we know all these angular values? Gamma O I know. I know the value of gamma O, it's the orthogonal rate. But if someone asks me how do I estimate beta, how do I estimate eta, etc. If you remember, in the last lecture we had established a relation between tan beta and zeta. Okay, tan beta and zeta. It was something like, if I remember correctly, tan beta is equal to cos gamma 0 by zeta minus sin gamma 0. Okay. So in one way at least I have an estimation of beta. But if you ask me what is the value of eta, do I know this? So in order to completely estimate the cutting forces, expression of the cutting forces in terms of the different tool geometry and other parameters of cutting, we need to do some more analysis. Secondly, what is PS? Do I have an estimate of PS? If I assume that PS must be equal to the stresses which are either equal to or crossing the shear strength of the material, then only failure must be occurring. So if I multiply the shear strength of the material with the cross section which is undergoing the shear, then I might be able to find out what's the expression of PS. So for that, if you notice, the chip is coming out this way. This is the chip coming out. What is this angle, for example? This is beta. What is this angle? This must be equal to eta, if you remember, eta O. So in that case there is this particular section which is undergoing shear. What is this section equal to? So if we look at the figure, if this be the tool, I hope it's visible, yes. This is the section that we are talking about. From looking from the top, on this particular view, the inclined section can be viewed. Okay, we are seeing a component of this particular section. So this distance, how much it is? How much is it? This one. So we have this to be equal to t by sin phi. What is this distance? This distance is this one, S0 sin phi. So S0 sin phi multiplied by t by sin phi gives me the projected area of this particular part. All right. So we can write that initial projected area is S0 sin phi multiplied by t by sin phi equal to S0 into t. So as the time of the lecture is already over, what we will do is we will continue with this thread only in the next lecture. So till then, Thank you very much. So, continue in the next lecture.